Hello and welcome to another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 7, Lesson 5 on ratios as fractions. Now we've worked a lot with ratios, and remember ratios are just a comparison of two quantities that can be scaled up or down using division or multiplication. All right, not addition or subtraction. So, we've looked at ratios and we've compared these quantities using things like tape diagrams and number lines and simply just scaling. Today we're going to look at two additional ways to represent ratios. One is just sort of a way of kind of shortcutting the number to number kind of system. But the other thing that we're going to do is we're going to just start to explore the connection between ratios and fractions. And that's a really, really important idea. So let's get into it right away. All right. Here we go. Ratios can be shown in many, many different ways, and one of the ways that they're shown in math, because mathematicians are like inherently lazy people. We want to shortcut everything by using symbols and crazy stuff like that. So let's talk about how ratios are sometimes shown with colons. All right. So if we have a quantity of A and a quantity of B, then the ratio of A to B is often shown as just A colon B. All right, and again, it's the colon literally just takes the place of the word to. All right, let's see how that pans out in exercise number 1. At a birthday party, the ratio of pizza slices to kids is 3:2, literally meaning for every 3 pizza slices, there are 2 kids, or vice versa, for every 2 kids, right, there are 3 pizza slices. I'm glad the ratio is that way. It would be scary the other way. All right, so in letter A, it says, if there are 12 kids, how many pizza slices are there? Fill in the table below to justify your answer. Okay, this is something that we've done many, many times. So what I'd like you to do is pause the video now and see if you can figure out with 12 kids how many pizza slices we have if the ratio of pizza slices to kids is 3:2. Pause the video now. All right, well, let's start it off. Now, again, we have to be very, very careful because it says pizza slices to kids is 3:2. We want to make sure down here when we start to fill out this table, we don't do 3, 2, 6, 4, etc. because for every 2 kids, there are 3 pizza slices. So we want to begin, let me just move this up to the top of the board. We want to begin by saying, okay, if there were 2 kids, there would be 3 slices. Now, if we double both of those, then for every 4 kids, there'd be 6 slices. Triple, we would get for every 6 kids, there would be 9 slices, etc. We can also do that deal with the tables where for every one of these columns, we're just going to increase by 2. So that's going to be 8, 10, 12, 14. And each one of these is just increasing by 3. So that's going to be 9 plus 3 is 12, then plus 3 is 15. Plus 3 is 18, plus 3 is 21. We still have to answer the question, right? If there are 12 kids, here's our 12 kids, how many pizza slices are there? There are 18. So that's how many pizza slices we need. 18 in order to have that 3:2 ratio, pizza slices to kids. Let's take a look at letter B. Using your table from A, make a plot of the points in the grid where the number of kids is the x-coordinate and the number of slices of pizza is the y-coordinate. All right, it's going to be a little bit tricky for me to keep everything on the screen at the same time. But what we're going to want to do here is we're just going to want to plot this relationship. All right, now you've got the table kind of sitting in front of you, hopefully, because you've got the worksheet. I'm going to just be kind of doing it in my head. Remember, if there were 0 kids, there would be 0 pizza slices. If there were 2 kids, there are going to be 3 pizza slices. 4 kids, there were 6 pizza slices. 6 kids, there were 9 pizza slices. 8 kids, there were 12 pizza slices. 10 kids, there were 15 pizza slices. 12 kids, there were 18 pizza slices. And that's actually all we're going to be able to fit on here. And what you'll notice every time when we make one of these graphs is that all the points, no matter how poorly I drew it, all the points fall in a nice straight line. That's kind of what happens when we're just scaling this up, because every time we're just going to add 2 more kids and 3 more pizza slices. 2 more kids, 3 more pizza slices, 2 more kids, 3 more pizza slices. It's actually identical to what we did in this table when I kept adding the 2's here and adding the 3's here. We get that constant ratio of 3 to 2. Now, letter D, quite important. Let's take a look at that one. According to the graph, how much pizza does a single kid get? How does this relate to the ratio? All right, so let's take a look at this, and I'd like you to pause the video now. Take a look at this graph. It's a little bit challenging. See if you can figure out how many pizza slices each kid gets based on this graph. Take a moment. Okay, so what do we have? Well, one kid, right, if we look very, very closely, gets 1.5 pizza slices. 1.5 pizza slices. Now, how does this relate to the ratio? Well, keep in mind, right, the ratio was 3 slices per 2 kids. And in fact, if we formed the fraction 3 divided by 2, or 3 halves, that would in fact be that 1.5 slices. And that starts to get us into the connection between ratios and fractions, right? In fact, if we formed this fraction, right, where the 3 was the number of slices and the 2 was the number of kids, and then we express that as a mixed number, or just by division, 3 divided by 2 is 1.5, right? Then that would show us how many slices each kid got. Finally, let's take a look at letter E. At a larger party, there are 30 kids. If the ratio of pizza slices to kids stays the same, how many pizza slices will be needed? All right, fantastic. Again, this is something that we've done again and again and again, and you have a lot of tools now to help you. Pause the video and see if you can figure out how many pizza slices there should be if there are 30 kids. All right, so let's do it. So we've got, I'm going to just do it by a simple scaling, all right? And by a simple scaling, what I mean is that if we've got 3 slices per 2 kids, right? And we're going to end up with 30 kids, right? Then how do I need to scale? Well, I would need to scale by multiplying those 2 kids by 15 to get up to 30 kids. Well, I have to do the same scaling here. So I have to do 3 slices times 15, and if I do 15 times 3 on my side of my paper, you know, or maybe you just know what 15 times 3 is, we would find that we need 45 slices. And that's it, right? So now let's take a look for the rest of the lesson at the connection between ratios and fractions. All right, well that didn't work at all. Let's try that again. All right, here we go. Ratios are oftentimes expressed as fractions, and in fact, we're going to see that time and time again as we move forward. All right, let's take a look at it for the first time really in exercise number 2. Exercise 2. In a 6th grade class, 3 out of every 5 students have brown hair. The ratio of students with brown hair to all students, therefore, is 3:5, or 3 to 5. Letter A just simply asks us to fill out the table below. All right, so this is simple enough, right? So if I had 5 students, 3 of them would have brown hair. Okay, that's what the ratio of 3 to 5 means, or 5 to 3 if you think about it as students to brown hair. That, of course, means that if I doubled, right, and I had 10 students, then I would have 6 of them with brown hair. If I tripled 15 students, then I would have 9 of them with brown hair. And if I quadrupled, i.e. multiplied by 4, then 20 students, and I'd have 12 with brown hair. All right, so simple enough, right? But now let's take a look at letter B. Form fractions from this table using the first row as the numerator and the second row as the denominator. All right, well, this is simple enough. All right, so let's also do this together. All right, I'm just suggesting, right, that we form fractions where we use this number up here as the numerator, the number in the top of the fraction, and all the numbers down here as the denominator, the numbers in the bottom of the fraction. All right, so the first one, quite easy, 3/5, right? 6/10, 9/15, and 12/20. Okay. Letter C. What does each fraction reduce to? All right. Well, if I looked at each one of the fractions up here, there's no way I can reduce 3/5, right? 3/5 is as reduced as a fraction gets. But the 6/10, if I divided both the numerator and denominator by 2, I'd be right back to 3/5. Likewise, the 9/15, right, if I divided the 9 by 3 and the 15 by 3, if I reduced them, I'd be right back to the 3/5. And the 12/20, if I divided the 12 by 4 and the 20 by 4, I'd be right back to 3/5. And of course that makes sense because how I got each one of these pairs was simply by taking the simplest ratio, right? 3/5 is the simplest form of this ratio, and just multiplying the top and the bottom by 2, the top and the bottom by 3, the top and the bottom by 4. So each one of these fractions reduces to 3/5. And in fact, that means we can really represent the ratio here of kids who have got brown hair to all kids as 3/5. And what does that really mean? It means that 3/5 of the kids have brown hair. It's really that simple. Now, how can we use, though, ratios represented as fractions to solve ratio problems? Well, take a look at letter D. If there were 40 students in the class, how many would have brown hair based on this ratio? Fill in the missing numerator below. Well, you've worked with equivalent fractions a ton, right? So the idea is very simple. Every single equivalent ratio will eventually reduce to 3/5. So if I'm kind of looking at this, right, and I know the total number of students is 40, right, then I just want an equivalent fraction to 3/5 that has a denominator of 40. Well, I can figure that out by thinking to myself, what would I have to multiply 5 by to get 40? Well, that would be times 8. What would I multiply 3 by? Well, it'd have to be the same thing times 8. So that will be 24/40. That will be the equivalent fraction, which means there must be 24 kids who have brown hair. And quite frankly, the majority of the time now that I try to solve ratio problems, I'm going to be using this idea of just two fractions that are equivalent to each other. Because you've gotten used to that both when you simplify fractions and when you add and subtract fractions and you have to get common denominators, right? Oftentimes when you simplify a fraction, that's when you're scaling down, right? When you're making the numerator and the denominator smaller by dividing by the same number. And oftentimes when you get common denominators, you're oftentimes taking a fraction and scaling it up, so to speak, by multiplying the top and the bottom by the same number. That's kind of what we did here. By changing 3/5 into 24/40, we're able to know that 24 of the kids must have had brown hair. Let's keep working with this idea in the next problem. All right, ratios as fraction. The ratio of A to B, or A colon B, can be represented in fraction form as A over B. All right, so when you look at sort of the ratio of A to B, then you're always, when put in fraction form, the first number in the ratio is the numerator, and the second number in the ratio is the denominator. All right, so let's play around with this in exercise 3. The ratio of girls to boys on a co-ed soccer team is 4:3. Represent this ratio as a fraction. Awesome. Well, this is pretty simple to represent as a fraction because, as I mentioned, right, you're going to put this in the numerator, this in the denominator, and therefore, as a fraction, the ratio is 4/3. Now, when we represent a ratio in fraction form, I will oftentimes, not always, but I will oftentimes include units. And here's what I mean by that. 4/3 is just a number, right? It's 1 1/3, 4/3, however you want to look at it. But I actually really like to include units in this case, right? And then the idea is the actual fraction bar is sort of the word per, right? So when I look at this ratio, I think 4 girls per 3 boys, all right? Now, you might think, it's like extra writing. Why do I want to put the girls and the boys? You know, it's confusing. Let's take a look at letter B to see why it might be nice to have these units there. If there are 12 boys, how many girls are there? Show how you found your answer. All right, so this is the simplest ratio, right? This is the simplest kind of ratio. We can't reduce it anymore. But if I want to think about this problem, again, keeping those units there, right, then this is helpful to have the units because then I know, if you will, that the boys go in the denominator, right? I got 4 girls to 3 boys is blank girls to 12 boys, or 4 girls per 3 boys is blank girls per 12 boys. And now it's relatively easy because I'm just thinking, kind of common denominators, what am I scaling by? Here, to go from 3 boys to 12 boys, I'd have to multiply by 4. And therefore, over here, I must also multiply by 4 to get that equivalent fraction, and I'd have 16 boys. All right. Let me just make sure. Oh, yeah, no, that's right. That's 16 girls. Otherwise, I have 16 boys and 12 boys. That's a little strange. No mistake in the multiplication there, just a little bit weird in how I answered the question. So yeah, 16 girls. All right, think about how comfortable you should be, I hope, with equivalent fractions and multiplying the numerator and the denominator of a fraction by the same thing. In this case, oftentimes with ratios, we sort of have to figure out what we're multiplying by. To go from 3 boys to 12 boys, I'd have to multiply by 4. So now I take 4 girls, multiply by 4, and I get 16 girls. Thankfully not 16 more boys. That would throw the entire problem off. All right, let's do one more like this and make sure you have the idea. Here we go. Exercise number 4. In a popular cereal, the ratio of marshmallow pieces to wheat squares is 2 to 7. If Elliot's cereal bowl contains 63 wheat squares, how many marshmallow pieces should it contain? Justify your answer. All right, well, what I'd like you to do is play around with this problem. Now, I know we've solved ratio problems in many, many different ways. So I'd like you to try to solve it using this idea of setting up the ratio as a fraction. Of course, you don't have to do it that way because we've seen many other ways to solve ratio problems, but since we're working with fractions right now, why don't you go ahead and give that a shot. Pause the video now. All right, so I'm going to go with the units again, right? So the initial ratio is 2. I always have to think about marshmallow and how to spell it. Marshmallows to 7 wheat squares. I just wish the ratio would be opposite, right? Then what do we know? Well, in the scaled up ratio, we know we have 63 wheat squares, right? And we need to figure out, right, how many marshmallow pieces we have. Well, again, just equivalent fractions, right? So if I'm going from a 7 in the denominator up to a 63 in the denominator, then I must have multiplied by 9, right? 7 times 9 is 63. I've scaled up this ratio by a factor of 9. I also then have to scale the numerator by a factor of 9, and that will give me 18 marshmallows. All right. Fractions are a fantastic way to think about ratios. Given that fractions can be scaled up and scaled down to create equivalent fractions, right, then it works exactly the same way as ratios being scaled up and scaled down. And there's other important connections. We're going to explore them more in the next lesson. All right. So today what we did is we actually saw 2 new things. We saw the colon representation of a ratio, and we'll see that a little bit on and off. We just want you to kind of get used to it here and there. Much more importantly though, we saw how ratios can be thought of in terms of fractions, where the first number in the ratio is the numerator of the fraction, and the second number in the ratio is the denominator of the fraction. We can then use the idea of equivalent fractions, both scaling them up and scaling them down, to solve a whole variety of ratio problems. We're going to work a lot more with ratios of fractions in future lessons. For now, I just want to thank you for joining me for another NGen Math 6 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.